All right, and thank you very much, Rupak. It was great seeing him again, seeing that name, the old familiar name on the agenda. We go back quite a ways at NASA. In any case, what I'm going to be talking about today, there might be a lot of people out here in the audience who have heard the phrase thermodynamics of computation before. It was a hot topic in like the 60s and the 70s. Rolf Landauer, Charlie Bennett, Wojciech Zurek, a bunch of people up at Los Alamos and other places. And they were interested in the fundamental limitations on what the thermodynamic characteristics of information processing are. The interesting thing, the work that was done then resulted in a lot of controversy, part of the reason being that it was all necessarily semi-formal. The reason it was semi-formal was because they, at the time, only had the tools of equilibrium statistical physics and near-equilibrium fluctuation dissipation theory. If nothing else, computational systems are far as hell from being equilibrium. So they could get as far as they did, and it was all very, very good work, but then it sort of got no further than that. Okay, now, simultaneously, about the past couple of decades, there actually has been a revolution in statistical physics. We now have essentially a complete theory of non-equilibrium statistical physics, arbitrarily far from equilibrium. It's all exact. The equations that I'm going to be putting up here are not idealized equations telling you what bounds would be if you were to do things quasi-statically, slowly. These are the exact equations for the cell phones in your pocket, for the HPCs that you're connecting to back home. And they tell you essentially everything that you might be interested in knowing. So anyway, there's a whole bunch of people that have started to realize that we can take all of this modern machinery that's being developed, non-equilibrium statistical physics, sometimes called stochastic thermodynamics, and revisit computation, and all this richness is unfolding. Just to point people to this, the NSF asked us to put together a wiki. Here's the address. Notice that's British spelling of center right there. It's got categories of papers from all fields, from cell biology to computer science theory to quantum computation and so on. I highly encourage people to visit it. It's a wiki, so please go there and improve it. So anyway, this is the work, as I should just say, by me and postdocs and many, many others. I'm just sort of summarizing it. What I'll try to do is present just two of the kinds of things that we're now figuring out. One of them having to do with circuits, what are sometimes called straight-line circuits, no loops or anything like that. And then much more abstractly, some work on Turing machines. Basically, what you could view as a correction to Kolmogorov complexity. So anyway, a lot of this will be familiar to people. About, depending on how you count, 5% energy usage in OECD countries goes to heat. So it's a very, very big deal. But it's not just a matter of a practical concern or an economic concern. Cells compute. A very interesting thing is that in each cell in you, right now, most of the energy burn is going to translation. That's in the ribosomes, where your DNA basically is turned into protein. The ribosomes operate about within 2 orders of magnitude of the thermodynamic optimum, which makes them about 10 to the 5th times better than all of these HPC systems we're talking about here today. Does this actually mean that nature had huge kinds of pressures on it to compute efficiently? And should that be incorporated into our models of population biology? Completely open question. You can even look at the biosphere as a whole. The energy coming into the biosphere is coming from the sun. That's it. We can calculate the free energy flux. We can do a really conservative, horribly rough estimate of the amount of computation being done in the entire biosphere, and the entire biosphere beats our computers. So there's lots to be understood by systems that are very, very different from the ones we might be normally thinking about. So anyway, without any further ado, let's talk a little bit about straight-line circuits, like this beast here. This is, by the way, Neil Gershenfeld. Back in '96, he actually did a really prescient article touching on some of these issues that I'll be talking about today. You can prove, it's not too difficult, that the actual heat produced by running an entire circuit is actually given by summing over all gates of the heat produced by that individual gate. So what we need to do is calculate the heat produced by each individual gate. And so here I'm now going to be presenting some of what's been discovered in non-equilibrium statistical physics. Assume we have a time-varying master equation, a continuous time Markov chain, a jump process, Fokker-Planck if you were to go to the continuum domain. This is like the standard model of how all non-quantum mechanical systems actually evolve in time, and you can actually extend it to quantum mechanical systems as well. So, for example, it characterizes stochastic dynamics in a genetic network. It also characterizes, even in the noise-free limit if you want to go there, dynamics of a digital gate in a circuit. Here is the first new result that was not there back in the 60s and 70s. Here is the conditional distribution of what the state of the system is going to be at, say, some t equals 1, given its state t equals 0. So you have a probability distribution, pipe it through that. That's the entire messy thing that your computer does, and out comes P1. If you look at the entropy of the distribution over states of your computer at time t1 minus time 0, you will get it's the sum of these two terms. The first one is these two things right here. That's the Shannon entropy drop. This term right here is called the entropy flow. Physically, you can think of entropy almost like a fluid flowing out of the system. This is going to be heat when you actually get down to brass tacks. This is what causes your circuits to melt. This is something that you want to be slow. This term right here, I haven't defined these yet, by the way. I'm just sort of giving you the properties. This one is called the entropy production. It's very simple use of some information theory to prove that entropy reduction cannot be negative. That is the reason for the second law. It's coming out of the mathematics of continuous time Markov chains. I've not given you any physics so far. This is all, in a certain sense, much more general. Okay, let me give you a particular example. Let's say that your system is evolving while connected to multiple heat baths. So now we're getting into physics, now we're getting into real HPCs. Make a technical assumption, what's called local detail balance, which almost always holds. Then the entropy flow is the actually heat flow in the conventional sense into the reservoirs. Because entropy reduction is non-negative, we have what is now called in the literature the generalized Landauer's bound, that the heat flow out of a system is greater than or equal to the drop in entropy of the states of the system as it evolves in time. These are all, that result is a greater than equal to. That gap between the actual thing on the left, the entropy flow, and this thing on the right can be huge in real systems. It is something that we could not get a handle on back half a century ago, but as I'll show you in a little bit, once I get past these introductory slides, we can now actually say a lot about it. So just to give an example of the generalized Landauer bound, let's say that your system is connected to only a single heat bath, which is almost never true, but never mind. Let's say it's a bit. It's only got two possible states. Let's say we're assuming that the distribution over the states of that bit before the process starts is uniform. And now let's do bit erasure. So we're taking a uniform distribution over the states of the bit. We're mapping it to a delta function. We're erasing that bit. Then the generalized Landauer bound, which says that the heat flow is greater than or equal to the drop in entropy. In this case, because your original distribution was uniform, your original entropy was log 2, your ending entropy is actually 0, so you get the total heat flow from the system is kT log 2, which is the conclusion that Rolf Landauer reached, intuited all those years ago. Okay, now back to exact equations for circuits. Here's the formula that we now have for the entropy flow, the heat coming out of a system, with this thing called entropy production. Now, here's something to realize. Let's look at this term right here, the drop in entropy. Let's fix your conditional distribution of one particular gate in your circuit. So I've got an AND gate, so it's always mapping P of x1 given x0 is going to be a delta function where x1 is an AND, logical AND, of whatever x0 happened to be. Take that AND gate, put it in different places in your circuit. There are going to be different initial distributions over the inputs into that gate, quite obviously. Therefore, because the actual conditional distribution the gate is implementing is fixed, the drop in entropy as you run through the gate will be different depending on where it is in the circuit. Since you can actually implement any Boolean function with an infinite number of circuits, this means that how you set it up, the wiring diagram, if you're using some universal basis, say ands, ors, and nots, the way that you actually put them together, because the input distribution to each gate is going to depend on the upstream gates, and therefore where you actually put it is going to drastically change the amount of entropy drop and therefore the heat that's being produced. These are not trivial effects, by the way. There's some other work by somebody called Stephanie Forrest, she's now at ASU, where it looks like these kinds of effects of just changing the wiring diagram is at least doing things very, very crudely on the order of tens of percent of the total heat produced by your system. So this is not just down in the noise of Boltzmann's constant. These are real large numbers. So anyway, different circuits all implementing the same Boolean function have different sum total of the Landauer cost. This gives you a new circuit design problem. It's a unpleasant, i.e. fun, circuit design problem. It's badly, badly global. Think about it. If I actually change the position or the characteristics of a gate way near the beginning, where the inputs come from, it's going to be changing the input distributions to all the downstream gates. So therefore, it's going to be changing how much heat is being produced by all of those downstream gates. So it's inherently global. Even solving this for very simple systems like 4 bits, closed form, believe it or not, nobody's actually been able to do so far. As I say, it's really annoying / fun, depending on which side of the bed you wake up on that morning. Okay, but here is something you can actually prove about it to illustrate how it's a global optimization problem. I'm going to introduce some new terminology. This is sometimes called synergy in the information theory literature. It's also called MultiInformation. It's a generalization of mutual information. What this says, if I've got a joint probability distribution over many, many different random variables, x1, ... the multi-information is the sum of the entropies of the marginals minus the entropy of the joint. It is quantifying how much information is shared among all those random variables. So let's take that general intuitive reasoning I was giving before about where you put a gate matters. Let's actually now calculate some things. When you run through a bunch of algebra, if you ask what is the objective function that you want to optimize in order to minimize the Landauer cost, this is just one of the 2 terms that gives you the total heat, the Landauer cost, the drop in entropy across all the gates in your system, this is what you get. If you have 2 particular circuits that are implementing the same function, C prime and C, G is running over the gates in the circuit, P of parents of G, that's the distribution, the joint distribution over the inputs of gate G. This is the multi-information. So basically what you want to do is design your circuit so that the summed over all gates, the inputs into the gates have as small multi-information as possible. We basically want them to be as independent. Loosely speaking, if I've got a gate in my circuit where the inputs in the gate give me no information about one another, then the thermodynamic cost, the amount of heat that I produce by running that gate, will be less. That's your overall goal in designing this circuit. Okay, let's see, so that's time remaining. Okay, so that was the first term that I was just talking about there. This equation, some of the multi-informations, that's giving you the total entropy the total entropy flow, the Landauer, generalized Landauer cost of running that circuit. Real circuits of entropy production. That is actually, in a real system, almost all of the heat used produced is over in this term. It's not sitting there down in Landauer's bound kind of range, which is why, frankly, everybody in this room has never needed to go through and really learn Landauer's and Bennett's and Zurich's papers, because that's all down at the level of Boltzmann's constant. This is the one that's actually driving real circuits, like the one that people are typing on as I speak. So in addition to knowing something about how the drop in entropy, the generalized Landauer cost, depends on the initial distribution, we need to know how the entropy production does. In other words, if I take the same gate, change the distribution of inputs into it, it's very straightforward to say what the actual change to the Landauer cost will be, what the change in the drop in entropy will be of that gate. But we also need to know what the actual effect on the entropy produced by that gate will be if we change its distribution over its inputs. That, in fact, is the primary driver of how hot to the touch that particular gate will be. So we've got to know something about that dependence. And so a couple of years ago, this was actually some work that I did with a postdoc. We actually calculated this, which had not been using this new machinery of non-equilibrium statistical physics. And here's the formula. This is actually saying that the entropy production, when you have an input distribution P0, it's now not the drop in entropies, it's the drop in Kullback-Leibler divergences as you go from P0 to P1, plus a term that's actually linear in P0. Intuitively speaking, roughly speaking, this is all of the nitty-gritty junk in your actual physical mechanism. This is why everything about your physical gate that means that it's not idealized, quasi-statically optimal. All of the teeny little imperfections and all of your resistance and all of that is in the entropy production term. So all of that actually can be reduced as far as dependence on the initial distribution your gate is concerned into this formula. If you add that formula there, this drop in KL divergences, Kullback-Leibler divergences, to the one before for the Landauer cost, which is the entropy. So you add this term, which I just showed you, to that term there, the drop in entropies. Your KL divergence plus entropy equals what's called cross entropy. So that's what we get right here. This is now the total heat flow. This is summing both the idealized drop in entropy, Landauer's bound kind of stuff, plus the real world, the real nitty-gritty. This is the total entropy flow out of any physical system you want to give me. I don't care. This is the exact equation for how the actual heat it produces varies depending on the input distribution that you give to that system. Now, to give an example of this term here, which is linear than P0, let's consider a wire, an interconnect, which of course is a huge source of heat. You don't even normally think of them as gates, but from a technical sense, they are. A wire, if it's idealized, it's going to be doing an invertible map. It's going to be having, here's the inputs to the wire, there's the output. So whatever your bit is, B, if you're going to start in state B of 0 after the wire runs, you're now going to basically flip them, and B is going to be in your output. Because that's an invertible map, it does not matter what the initial distribution is. You can very easily satisfy yourself that the drop in entropy, no matter what your distribution is, over possible values of B, the drop in entropy of running a wire is 0, because it's invertible. You can also satisfy yourself, it takes a little bit more work. Again, it doesn't matter what your distribution is, that the drop in Kullback-Leibler divergences is 0 for a wire. So what this tells us is that in wires, in those little interconnects, in point of fact, all of the heat that they produce is a linear function of the distribution of bits that goes into that wire. And again, this is exact. This is not an approximation. This is something that somebody could go off and measure in a lab. Okay, so anyway, in the interest of time, let me run through this now a little bit. So here is, again, this is the entropy flow out of a single gate. We need to evaluate this for each wire and gate in a circuit, because a wire is a gate, and then just sum. And so this now is the answer for, if you take into account everything, not only the idealized Landauer's bound, but also the real detailed entropy production. This is your overall optimization problem. Obviously, it should go without saying that in the entropy production terms, if you look at things like these right here, those are parameters of your physical system. You're not going to know what those are typically a priori. They're going to be characteristics of your actual gate. So that's where the real world is coming in, is in things like what's called here EP of Q0C cryptically. That's something that you will not be able to calculate from first principles, as opposed to something like the Landauer cost, which is just the drop in entropy. But so anyway, assuming that you either measure those in the lab or get them some other way, you now have another circuit design optimization problem. This is the one for your actual real-world circuit, not just an idealized Landauer bound. So anyway, as I say, all this is exploding. There are many people working on these kinds of things. You can apply it in computer science, to circuit complexity theory. You can apply it to logically reversible circuits. Turns out that they actually don't have the precise advantages that people thought they did. It's a slippery issue. But anyway, there's huge amounts that can be done there. And I guess I got 2.5 minutes, so let me very, very briefly then say something about what happens when you take some of all this modern physics and apply it now to analyze the thermodynamics of Turing machines. A Turing machine is not a circuit, but nonetheless, you can view it as just as a system that happens to have a countably infinite number of states that's updating according to a transition rule. You can imagine trying to instantiate one in a physical box, where you, of course, make the usual trick of saying, well, yes, it's got a finite memory, but we're assuming it can always get access to other memory if needed, and start calculating things. So, for example, as everybody knows, the Kolmogorov complexity of a bit string, if you're measuring it on a universal prefix Turing machine, is the minimum length of any input program, any input bit string that you feed into that Turing machine that causes it to actually compute your bit string V and halt. Beautiful, beautiful mathematics associated with these things. The book of Lee and Vitani, of course, is the go-to source for all that. But now that's sort of aesthetic. As I said, it's beautiful, Kolmogorov complexity, but it's not really motivated beyond that. It's, in a certain sense, it's math. It's gorgeous math. I would say it's some of the most profound philosophy we human beings have created, but that's sort of, in a certain sense, the extent of its motivation. Well, let's get a little bit more practical and say that we're a little bit more like engineers and define something called the thermodynamic Kolmogorov complexity of computing bit string V. That's going to be the minimum over all bit strings of the heat produced by running that Turing machine to compute the bit string V and then halt. Okay? Because any computer, when it runs, produces heat. So what's the actual answer? Well, it turns out that if V is your bit string, the minimal amount of entropy flow, it's the Kolmogorov complexity plus 2 correction terms. That one, Z right here, this is using kind of physicist notation. You might have seen that before as omega. That's Chaitin's constant, Chaitin's omega. And this is something that's got to do with your actual distribution over inputs to your Turing machine. It's sometimes called the universal distribution in the Turing machine literature. One of the fascinating things about this particular correction is that when you add these things together, it's bounded. It doesn't matter what V is. So Kolmogorov complexity is unbounded. If I give you an arbitrary bit string, then the Kolmogorov complexity can be as large as you want. But the thermodynamic Kolmogorov complexity, actually, it turns out, has got an upper bound, though, of course, it's an uncomputable one. So anyway, there's a huge amount here to be done. I'm sort of just giving you a snapshot of some of the results. Some things to just jot down. Here's that wiki again with the British spelling. Please visit it and start to add material. There's a new book that will be coming out, should be within several weeks now. Invited chapters that we edited, me and some of my collaborators. And this paper is an invited review that I just finished, and that's, I'm told, will actually appear in the online version of the journal at the end of this week. So I'll end it there. Thank you very much.
Any questions?
Do you want to try, or?
There are several questions on this side, sir.
Back there, I think.
Hi, yeah, that was a fascinating talk. It seems like you've characterized the way to calculate the entropy of a given circuit. Are there any insights that this process would give you how to better design a circuit to drive entropy down? And also, does it say anything about perhaps how to implement, better gate design and maybe even think about faster algorithms so you don't have to go, reducing circuit depth and things like that?
Yep. Yeah, so certainly in terms of the usual ways that you would measure the complexity of a circuit, its depth, its size, and things like this, this suggests a whole bunch of new ways of actually characterizing the complexity of a circuit. We do not right now know exactly how the thermodynamic circuit complexity relates to conventional circuit complexity. All of those issues, the several PhD theses there to be done. To answer your question, I probably ran through it too quickly, but for example, the simplest answer is in the idealized case, where you actually have perfect gates which don't have any annoyances of actually producing heat, just like wires do if they're just doing the reversible function. In that case, the Landauer's bound case, what you want to do is lay out your gates in your circuit that's implementing your desired Boolean function in such a way as to minimize the sum over all of those gates of this multi-information of the inputs to those gates. So very nasty coupled global problem. If you instead want to look at real circuits, not just the idealized one, your optimization problem now becomes this, where that's now cross entropies, and now because it's the real world, you've got these things here, these mysterious Qs, which I haven't talked about, which are actually parameters that characterize your physical system. That's the nitty-gritty. That's the sand in the cogs in the wheel, is going into that Q. So if you're good about it, you can maybe actually calculate Q a priori with some kind of detailed modeling of the physics. Alternatively, you can imagine actually estimating it in the lab. But once you have the Q for each of your gates separately, then your problem is figure out how to actually wire the whole thing up so that the sum of the gates of this drop in, that's cross entropy, as you run the gate is minimized.
So here's
Okay.
great talk. So you talked about how nature has optimized this for the cell. And I'm assuming that over natural selection and everything, they've had a few million years in order to be able to optimize it to get to such a thing. Does that limit the way that a cell could evolve in a living system?
That is a huge question. It's actually billions of years, not millions of years. But in essence, what we have right now, to be very, very careful about it, it suggests that, but here's the thing. It could be that any chemical reaction network that you put together that performs the function of translation, it could just be that all of them are massively thermodynamically efficient. So we don't actually know. If I randomly sample over the space of chemical reaction networks that implement what a ribosome does that give me a prior which is somehow so biased towards high efficiency that it swamps this likelihood so it almost doesn't matter what nature did, it would have come up with something efficient? Or is it the case that actually natural selection really was working like a banshee to try to get that thermodynamic efficiency as good as possible? We think very strongly the latter, and I'm working with some people who actually do a lot of stuff with real live chemical reaction networks that we're trying to get a handle on that quote prior, but we don't formally know. But here's the follow-up to your question. Let's even just assume, it seems reasonable, that that thermodynamic cost, because the cell, never mind the heat it's producing, it's got to go off and eat that many more ice cream sundaes to be able to do its business if it's not efficient. Because that heat is all coming from those ice cream sundaes that the cell is eating. So what that suggests is it should have a huge effect on fitness, essentially as you're saying, and that therefore all of population biology, the neo-Darwinian synthesis, should have this extra term put in there, depending on what the computation is that the cell is doing. To give another example, it has to do with biology. That's 20% of my calorie burn is in my brain, and it's in your brain. That's a massive fitness cost. Is that the reason why human-level intelligence is so rare in the evolutionary record? And what happens if we try to, some people are trying to do this, it's outside of my expertise by far, but some people are trying to investigate neurobiology circuitry, thinking about in terms of the need to be thermodynamically efficient, because the brain is vastly more efficient, obviously, than any of our artificial computers are right now. So it's got implications all over biology.
So the question I would have then is, can I manipulate it so that, because cancer is in a slightly different state and uses up more energy and seems to be less efficient, can I rearrange it so that I could actually combat that? Yeah.
I hadn't thought of that. There's all kinds of, that's a very good idea. I don't know. Don't know.
Any other burning questions right now? Okay, I have a burning question.
Okay.
So you and I talked about this a little bit, and a lot of this is fundamental research. When will we see some of these things actually coming into practice in chip designers and folks like that will pay attention to this?
So far, yeah. So far, it's all been, basically, this part of it has been mathematics and theory. In other parts of non-equilibrium statistical physics, a lot of the fundamental equations of this new field, they have been tested. There are many covers of Nature and of Science that are basically new kinds of experiments validating all this new mathematical machinery. This is so new that we haven't yet thought of even putting together the first experiments to basically prove that the algebra is correct. There are some people, as I mentioned, Stephanie Forrest, who's working at abstract levels where you have basically chip simulators to try to see how rearranging the chip might get at some of these things. But as far as using it to build real systems, well, if you're to give as much money as going to, say, some of the quantum computation, it could go much, much faster. But realistically, it's going to be probably 5 years before they'll start to see articles where people are talking about putting together very, very simple circuits with these kinds of ideas.
Okay, very good. Well, thanks again, David.
Okay, thank you.